Imagine this: a city, gleaming with towers of glass and steel, roads stretching for thousands of miles, satellites orbiting overhead, plastic in the oceans, carbon in the atmosphere. A civilization at its peak. Now imagine that civilization disappearing. Not gradually, suddenly, everyone gone, every human trace left behind to face the relentless forces of geology, erosion, and time. How long would it take for every trace of that civilization to vanish completely? 1,000 years? 10,000? A million? The answer is more unsettling than you might think. And it leads us to one of the most profound questions in planetary science. If an industrial civilization existed on Earth millions of years, if we're humans, would we even know? In 2018, two scientists asked exactly that question. What they discovered didn't just challenge our understanding of Earth's past. It changed how we search for alien civilizations across the universe. This is the story of the Silurian Hypothesis. And by the end of this investigation, you'll never look at Earth's 4.5 billion year history the same way again. The year was 2018. The scientists, one from NASA, one from the University of Rochester, were having a conversation that would ripple through the scientific community. Dr. Gavin Schmidt is the director of NASA's Goddard Institute for Space Studies. He's one of the world's leading climate scientists, specializing in how human activity affects Earth's climate. His colleague, Dr. Adam Frank, is an astrophysicist who studies how civilizations interact with their planets, a field called astrobiology. They weren't looking for evidence of ancient aliens, they weren't pursuing fringe theories. They were asking a simple, scientifically rigorous question: how would we detect an ancient to industrial civilization in the geological record? The question emerged from their work on climate change and the search for extraterrestrial life. If we want to find evidence of alien civilizations on distant planets by studying their atmospheric composition, looking for pollution, greenhouse gases, signs of industry, we need to understand what those signatures look like over deep time. So they turned the question back on Earth itself. What if there was an industrial civilization here, on our own planet, tens or hundreds of millions of years ago? What evidence would survive? And critically, would we recognize it? They published their findings in the International Journal of Astrobiology. The paper's title was straightforward: The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The name came from Doctor Who, a British science fiction series featuring an ancient reptilian species called Silurians who supposedly evolved intelligence before humans. It was a playful reference, but the science behind it was deadly serious. What Schmidt and Frank discovered was unsettling. If a civilization existed on Earth more than a few million years ago, we might have almost no way to detect it. And that realization has profound implications not just for Earth's past, but for the future of our own civilization. Let's be clear about what the Silurian Hypothesis is and what it isn't. It is not a claim that another civilization existed before humans. Schmidt and Frank found no evidence of pre-human, industrial societies. They're not suggesting dinosaurs built cities or that ancient reptiles developed technology. Instead, it's a thought experiment, a rigorous scientific exploration of a single question: if such a civilization existed, how would we know? The hypothesis examines the limits of detectability in the geological record. It asks, what traces does an industrial civilization leave behind? How long do those traces last? And what would remain after millions of years of geological processes? The implications extend far beyond Earth. If we're searching for alien civilizations by studying the atmospheres of distant planets, looking for technosignatures like industrial pollutants, we need to understand how long those signatures persist. A civilization might have risen and fallen millions of years before we pointed our telescopes at their planet. Would we see any evidence? The Silurian Hypothesis forces us to confront an uncomfortable truth. The geological record is incomplete. Time erases almost everything. And what we think of as permanent human impacts, cities, roads, plastics, even nuclear waste, might vanish far faster than we imagine. So before we explore whether another civilization existed on Earth, we need to answer a more fundamental question: how long will your civilization be detectable? Let's start with the present. What evidence is humanity leaving behind? Right now, humans are transforming the planet at a scale unprecedented in Earth's history. We've moved so much rock and sediment that geologists have proposed a new geological epoch, the Anthropocene, the age of humans. The markers are everywhere. We've produced over 8 billion tons of plastic since the 1950s. Much of it has broken down into microplastics that now permeate oceans, soils, and even the atmosphere. We've detonated over 2,000 nuclear weapons, leaving radioactive isotopes in sediment layers worldwide. We've extracted and burned fossil fuels, releasing carbon dioxide that's changing the atmosphere's composition. We've driven species extinct at rates not seen since the asteroid that killed the dinosaurs. We've also left physical structures, cities covering millions of square kilometers, roads, bridges, dams, the Great Wall of China, the pyramids, skyscrapers in every major city. Surely these will last forever, right? Not even close. Consider New York City. If every human vanished tomorrow, what would happen? Within decades, vegetation would reclaim the streets. Within centuries, most buildings would collapse, steel corrodes, concrete crumbles, glass shatters. Within a few thousand years, the landscape would look wild again, with only subtle irregularities in the terrain suggesting something was once there. The Panama Canal, it would fill with sediment, Mount Rushmore. Erosion would smooth the faces within tens of thousands of years. Even our most ambitious structures, Hoover Dam, the Channel Tunnel, would become unrecognizable within a few 100,000 years. And that's just the beginning. Now extend that timeline to millions of years. Add plate tectonics, the movement of Earth's crust that recycles surface rock into the mantle. Add erosion, sedimentation, chemical weathering. Add the fact that 70% of Earth's surface is ocean, where most human activity is inaccessible to future geologists. After 50 million years, our cities would be gone. Our plastics would have degraded into unrecognizable chemical traces. Our satellites would have fallen from orbit and burned up. Even our radioactive waste designed to be detectable for thousands of years would have decayed or been buried under kilometers of sediment. What would remain? That's the question Schmidt and Frank set out to answer. And the answer is both fascinating and terrifying. But before we explore deep time and what survives it, let's take a moment. If you're captivated by questions that challenge how we see our place in Earth's history, if you want to explore more evidence-based mysteries about our planet and the universe, consider subscribing. We're building a community that believes real science is more profound than any fiction. And there's so much more to uncover together. Now, let's look at what actually survives millions of years. The geological record is a chronicle of Earth's 4.5 billion year history. But it's not a complete chronicle. It's fragmentary, biased, and full of gaps. Here's why. Most of what happens on Earth's surface doesn't get preserved. Fossilization is rare. Less than 1% of all species that ever lived left fossils. Rock layers get eroded, subducted into the mantle, metamorphosed beyond recognition. The older the rock, the less likely it is to survive intact. In fact, Earth's surface is constantly recycling itself. Plate tectonics ensure that oceanic crust, where most marine life lives and dies, gets subducted back into the mantle within 200 million years. Continental crust lasts longer, but even it gets worn down, buried, and transformed. The result? Most of Earth's surface is geologically young. Very few exposed rocks are older than 500 million years. The oldest surface rocks found in Western Australia and Canada date back about 4 billion years, but these are rare exceptions. For context, dinosaurs went extinct 66 million years ago. If they had somehow developed an industrial civilization, absurd. But bear with me, most of the surface they lived on no longer exists. It's been subducted, eroded, or buried under kilometers of sediment. So what does survive deep time? What markers could a pre-human civilization leave that would still be detectable today? Schmidt and Frank identified several possibilities. But to understand them, we need to journey way back through Earth's history. We need to explore the 4.5 billion years that came before us. Let's put Earth's history in perspective. If we compressed Earth's entire 4.5 billion year history into a single 24-hour day, here's what it would look like. Midnight. Earth forms from the solar nebula, a cloud of dust and gas orbiting the young sun. 3 a.m. The first primitive life appears, simple single-celled organisms in the oceans. 9 p.m. Complex multicellular life emerges. 10:30 p.m. The Cambrian explosion, sudden diversification of animal life. 11 p.m. Fish evolve. 11:30 p.m. Plants colonize the land. 11:40 p.m. Dinosaurs appear. 11:50 p.m. Dinosaurs go extinct. 11 hours 58 minutes and 43 seconds p.m. The first hominids appear in Africa. 11 hours 59 minutes and 58 seconds p.m. Modern humans emerge. 11 hours 59 minutes 59 seconds and 7 milliseconds p.m. Written history begins. Everything humans have done: agriculture, cities, the Industrial Revolution, space exploration happens in the last tenth of a second before midnight. We are unimaginably recent, and that gives us a skewed perspective. We think of Earth as static and changing, but Earth has been dynamic for billions of years: continents drifting, climate shifting, life evolving and going extinct in massive pulses. And here's the key question the Silurian Hypothesis raises. In all the time, all those billions of years, is it really impossible that intelligence emerged before us? Let's examine when another civilization could have theoretically existed. First, we can rule out the early Earth. For the first billion years, the planet was inhospitable molten rock, a toxic atmosphere, no oxygen. Life itself didn't emerge until about 3.8 billion years ago, and even then it was simple, single-celled organisms. There's no possibility of complex life, let alone intelligence. We can also rule out most of the next 2 billion years. Earth's atmosphere lacked oxygen until about 2.4 billion years ago, the Great Oxidation Event. Complex life requires oxygen for the energy metabolism needed to support large bodies and brains. No oxygen, no complexity. So the realistic window for complex intelligent life begins around 600 million years ago, during the Ediacaran period, when the first multicellular organisms appeared. From that point onward, life exploded in complexity. Let's focus on the major eras. The Paleozoic era, 541 to 252 million years ago. This era saw the colonization of land by plants and animals. Fish evolved into amphibians, which evolved into reptiles. By the end, the supercontinent Pangaea had formed. Could intelligence have emerged here? Theoretically, yes, though life was still relatively simple compared to what would come later. The Mesozoic era, 250 to 266 million years ago, the age of dinosaurs. For 186 million years, dinosaurs dominated the planet. They evolved into an astonishing diversity of forms, some as small as chickens, others as large as buildings. Some were remarkably intelligent, with brain-to-body mass ratios comparable to modern birds. Could dinosaurs have developed civilization? We'll explore that question in depth shortly. The Cenozoic era, 66 million years ago to present. After the asteroid impact that killed the dinosaurs, mammals diversified rapidly. Primates evolved, then hominids, then humans. This is our era. But here's what's important. Each of these eras spans tens to hundreds of millions of years. That's an immense amount of time. Humans have existed for about 300,000 years. Industrial civilization for about 250 years. That's a geological eye blink. If another species developed industrial-level intelligence for even a brief period, say 100,000 years, and then went extinct 50 million years ago, would we find evidence? To answer that question, we need to understand how fossilization works and how rarely it happens. When an organism dies, it usually decomposes completely. Bacteria, scavengers, and weathering break down soft tissues within days or weeks. Bones and shells last longer, but even they typically disintegrate within a few thousand years. Fossilization requires very specific conditions. The organism must be buried quickly, usually by sediment in a lake, river, or ocean. Oxygen must be excluded to prevent decay. Over time, minerals seep into the bones or shells, replacing organic material with stone. This process, called permineralization, can take thousands to millions of years. The result is a fossil, a mineralized replica of the original organism. But here's the catch. Only a tiny fraction of organisms get fossilized. Most die in environments where fossilization can't occur on land, exposed to air and scavengers. Even in ideal environments, the odds are slim. Paleontologists estimate that less than 0.1% of all species that ever lived left fossils, and even when fossils form, they must survive. Geological processes destroy most fossils before they're ever found. Rock layers get eroded, subducted, or heated and metamorphosed, obliterating the fossils within. The result, the fossil record is spectacularly incomplete. We have fossils of maybe 1 in 1,000 species that ever existed. For many entire groups of organisms, we have 0 fossils. The record is biased toward organisms with hard part shells, bones, teeth, and toward environments where sedimentation occurs rapidly, like river deltas and shallow seas. What does this mean for detecting a pre-human civilization? If that civilization lasted only a few thousand years, even a few 100,000, the chances of finding fossils of its members are vanishingly small. We have fossils of millions of individual dinosaurs, but they existed for 186 million years. A short-lived civilization would leave almost no trace in the fossil record. But fossilization isn't the only way evidence can be preserved. There are other markers, chemical signatures, isotopic anomalies, stratigraphic layers that show something unusual happened. And that's where the Silurian hypothesis gets interesting. If physical fossils are unlikely, what about chemical evidence? Industrial civilizations leave distinct chemical fingerprints. We can see this in our own impact on Earth. Since the Industrial Revolution began around 1750, we've fundamentally altered the chemistry of the atmosphere, oceans, and even deep sediments. Here are the markers. Carbon isotopes. When we burn fossil fuels, we release carbon dioxide that's depleted in carbon-13, a heavier isotope of carbon. This creates a distinct signature in the atmosphere and in organisms that absorb that carbon. Future geologists could detect this shift in carbon isotopes in sediment layers dating to the Anthropocene. Nitrogen and phosphorus. Industrial agriculture uses massive amounts of synthetic fertilizers. These chemicals wash into rivers and oceans, creating dead zones where algae blooms consume all the oxygen. This process called eutrophication leaves chemical signatures in sediment layers. Heavy metals and rare earth elements. Mining and industry concentrate certain metals: lead, mercury, cadmium in the environment. These accumulate in soils and sediments. Additionally, technologies like electronics and batteries use rare earth elements that don't occur naturally in high concentrations. Plastic polymers. While plastics degrade over thousands of years, they break down into microplastics that persist much longer. Some chemists speculate that certain plastic-derived compounds could survive for millions of years as chemical fossils. Radioactive isotopes. Nuclear weapons testing in the 1940s-60s left traces of plutonium-239, cesium-137, and other isotopes worldwide. These isotopes are rare in nature, so their presence in sediment layers is a clear marker of human activity. Some have half-lives of thousands to millions of years. Synthetic molecules. Humans have created thousands of molecules that don't exist naturally: pharmaceuticals, pesticides, industrial chemicals. Some of these might persist as trace compounds in the geological record. These are the markers of an industrial civilization. And critically, some of them could survive for millions of years. But here's the question. If we found these same markers in ancient sediment layers, carbon anomalies, nitrogen spikes, concentrations of rare metals, would we recognize them as evidence of a past civilization? Or would we assume they were natural fluctuations? Schmidt and Frank found a case study that offers a chilling answer. About 56 million years ago, something catastrophic happened to Earth's climate. Over a period of just a few thousand years, at geological instant, global temperatures spiked by 5 to 8 degrees Celsius. The oceans warmed, ice caps melted, sea levels rose. Massive amounts of carbon dioxide flooded the atmosphere. Ocean chemistry changed, causing widespread extinctions of deep-sea organisms. This event is called the Paleocene-Eocene thermal maximum, or PETM. It's one of the most dramatic climate disruptions in Earth's history. And geologists can see its fingerprint in sediment cores from around the world. The PETM left several distinct signatures. A carbon isotope excursion. Sediment layers from this period show a sharp decrease in carbon-13 relative to carbon-12, the same signature that burning fossil fuels creates today. Global warming markers. Isotopes in fossilized shells show that ocean temperatures rose rapidly. Ocean acidification. The sudden influx of CO made the oceans more acidic, dissolving the shells of many marine organisms. This shows up as a gap in the fossil recorded dissolution horizon where carbonate fossils disappear. Ecological disruption. Many species went extinct. Others migrated toward the poles, terrestrial ecosystems shifted dramatically. The PETM lasted about 200,000 years before the climate gradually returned to normal. The cause has been debated, but most geologists believe it was triggered by volcanic activity that released massive amounts of carbon from underground reservoirs, possibly methane hydrates on the ocean floor. But here's what's striking. If you didn't know the PETM was natural, you might interpret it as evidence of an industrial civilization, a sudden carbon isotope excursion. That's what burning fossil fuels does: ocean acidification, industrial pollution, global warming, greenhouse gas emissions, ecological disruption, habitat destruction, and pollution. The PETM looks almost exactly like what our own civilization is doing to the planet right now. And that raises a disturbing question. Schmidt and Frank do claim the PETM was caused by a pre-human civilization. The scientific consensus is that it was a natural volcanic event, but they use the PETM as a thought experiment. If the PETM had been caused by an industrial civilization, how would we tell the difference? The answer is troubling. We might not be able to. Here's why. The markers of industrial activity: carbon isotope shifts, warming, acidification, ecological destruction can all occur naturally. Volcanoes release CO, asteroid impacts cause mass extinctions. Natural climate cycles shift temperature and sea level. To definitively identify a civilization, you'd need to find markers that can only come from intelligence, things like synthetic molecules that don't occur naturally. But after millions of years, would those molecules survive? And would we recognize them? Anomalous concentrations of rare elements. But natural geological processes can concentrate elements too. Structures or artifacts. But after tens of millions of years, with plate tectonics and erosion, would any structure survive? The PETM shows us that even a dramatic signal in the geological record can be ambiguous. Natural processes can mimic artificial ones, and time erases the fine details that would let us distinguish between them. This is the core insight of the Silurian hypothesis. The geological record might contain evidence of past civilizations, but we might not recognize it, or we might dismiss it as natural variation. And there's another layer to this. The PETM wasn't the only climate disruption in Earth's history. There have been others, some even more severe. Let's look at a few other events in Earth's history that show similar patterns. The Torsion Oceanic Anoxic Event 183 million years ago. During the Jurassic period, a massive pulse of volcanic activity released huge amounts of CO. Ocean temperatures spiked. Oxygen levels in the deep ocean plummeted, causing mass extinctions. The carbon isotope record shows a dramatic excursion similar to the PETM. The end Permian mass extinction 250 million years ago. The worst mass extinction in Earth's history. About 96% of marine species and 70% of terrestrial species went extinct. The cause is debated, but likely involved massive volcanic eruptions in Siberia, which released enough CO to trigger runaway global warming. Ocean acidification, anoxia, and ecological collapse followed. Snowball Earth events multiple times between 720 and 580 million years ago. Earth's climate became so cold that ice sheets covered the entire planet, even the equator. These events were eventually reversed by volcanic CO building up in the atmosphere since ice-covered oceans couldn't absorb it. The recovery phase would have involved rapid warming, another carbon anomaly in the geological record. Each of these events left chemical and geological signatures similar to what an industrial civilization might leave. Carbon spikes, warming, extinctions, ocean chemistry changes. Does that mean any of them were caused by civilizations? Almost certainly not. The scientific explanations, volcanism, asteroid impacts, natural climate feedbacks, are well supported by evidence. But here's the point. If a civilization did exist during one of these periods and contributed to the climate disruption, we might never know. The signal would be buried in the nose of natural processes. And that leads to an even deeper question. If we can't detect a past civilization on Earth, our own planet, where we have direct access to the rocks, how would we ever detect one on an exoplanet light years away? This is where the Silurian hypothesis connects to the search for extraterrestrial intelligence. For decades, scientists have searched for extraterrestrial intelligence by listening for radio signals, messages deliberately sent by alien civilizations. This is the work of SETI, the search for extraterrestrial intelligence. But in recent years, a new approach has emerged, looking for technosignatures indirect evidence of advanced civilizations visible in the light from distant planets. Here's how it works. When we observe an exoplanet, we can analyze the spectrum of light passing through its atmosphere. Different molecules absorb light at specific wavelengths, creating a fingerprint. By studying this fingerprint, we can determine what gases are present. Most exoplanet atmospheres show the gases we'd expect: hydrogen, helium, water vapor, carbon dioxide, methane. But what if we detected gases that shouldn't be there naturally? What if we found industrial pollutants, chlorofluorocarbon CFCs, nitrogen dioxide, or other synthetic compounds? That would be a technosignature evidence of an industrial civilization. But here's the problem the Silurian hypothesis exposes. Technosignatures might be short-lived. Imagine a civilization on a distant planet. They industrialize, polluting their atmosphere with greenhouse gases and synthetic chemicals. But then after a few thousand years they collapse. Maybe they destroy themselves in war. Maybe they exhaust their resources. Maybe they transition to cleaner technologies. Whatever the cause, the pollution stops. And over the next few thousand years, natural processes reign, chemical reactions, biological absorption remove most of the pollutants from the atmosphere. If we pointed our telescopes at that planet a million years later, would we see any technosignatures? Probably not. The atmosphere would look natural again. This is the detectability problem. Civilizations might be common, but if they leave detectable atmospheric signatures for only a brief window a few thousand years out of billions, the chances of us observing one at the right moment are vanishingly small. The Silurian hypothesis forces us to confront this reality. If we can barely detect the signatures of human civilization after just a few million years on Earth where we have direct access to the rocks, how can we expect to detect alien civilizations from light years away, observing only their atmospheres? This brings us to the Fermi paradox, one of the most famous questions in science. In 1950, physicist Enrico Fermi asked a simple question: where is everybody? Here's the paradox. The universe is vast, 100 billion galaxies, each containing 100 billion stars. Many of those stars have planets. Some of those planets are in the habitable zone where liquid water can exist. Given the sheer number of possibilities, intelligent life should be common. So why haven't we detected any aliens? Why haven't they visited Earth? Where are all the radio signals, the megastructures, the evidence of advanced civilizations? There are many proposed solutions to the Fermi paradox. The Great Filter. Maybe there's a barrier that prevents most civilizations from reaching advanced stages. Perhaps intelligent life is rare, or perhaps civilizations tend to destroy themselves before they can colonize the galaxy. The Zoo hypothesis. Maybe aliens exist but are deliberately avoiding contact with us, observing us from afar like zoo animals. The Dark Forest hypothesis. Maybe civilizations stay silent because announcing their presence is dangerous. We're early. Maybe intelligent life is rare, and we're among the first civilizations to emerge in the universe. The Silurian hypothesis adds another possibility. Maybe civilizations are common, but they're hard to detect because they don't last long and their signatures fade quickly. If industrial civilizations typically last only a few thousand to a few 100,000 years before collapsing or transitioning to less detectable technologies, then the universe could be full of civilizations we'd never see. Their atmospheric technosignatures would have faded. Their radio signals would have stopped. Their physical structures would have eroded. We might be surrounded by the ghosts of dead civilizations and never know it. This is perhaps the most sobering implication of the Silurian hypothesis. It suggests that the silence of the universe might not be because intelligence is rare. It might be because intelligence is fragile, and the evidence of its existence fades fast. Let's think about what traces an alien civilization might leave that could survive for millions of years. On Earth, we've identified several markers that might persist: geological anomalies, concentrated rare elements, synthetic isotopes, unusual chemical layers in sediment, orbital debris. Satellites and space junk in stable orbits might survive for millions of years, though most low Earth orbit objects eventually fall and burn up. Moon or asteroid bases. Unlike Earth, the Moon and asteroids have no atmosphere, weather, or plate tectonics. Structures there would erode much more slowly. A lunar base could theoretically remain recognizable for billions of years. Biological changes. If a civilization genetically engineered organisms or caused major extinctions, those changes might show up in the genetic and fossil records. On other planets, the situation would vary. Rocky planets with active geology like Earth, traces would fade quickly due to plate tectonics and erosion. Rocky planets with dead geology like Mars, structures and artifacts could survive much longer. Mars has no plate tectonics and only a thin atmosphere. A Martian civilization's ruins could remain visible for hundreds of millions of years. Gas giants. Civilizations couldn't arise on gas giants themselves, but they might build floating cities or mine atmospheric gases. Evidence would be even harder to detect. Moons of gas giants. Icy moons like Europa or Enceladus have subsurface oceans. If life or civilization arose there, their traces would be buried under kilometers of ice we'd need to drill through to find them. The key insight: different planetary environments preserve evidence differently. On Earth, our active geology erases most traces. But on geologically dead worlds, evidence could last much longer. This has implications for future space exploration. If we want to search for past civilizations in our own solar system, we should focus on the Moon, Mars, and asteroids where traces would survive longest. In fact, some scientists have proposed doing exactly that. Let's entertain the possibility seriously. Could an industrial civilization have existed on Earth before humans? Here are the arguments in favor. 1. Deep time is vast. Earth has been habitable for at least 600 million years, possibly longer. Complex life has existed for over 500 million years. That's an enormous window. Humans have existed for 300,000 years, 0.05% of that time. 2. Intelligence has evolved multiple times. Intelligence isn't unique to humans. Octopuses, corvids, crows and ravens, parrots, elephants, and cetaceans, dolphins and whales all show sophisticated problem-solving and social behaviors. Intelligence can evolve independently in different lineages. 3. Tool use isn't unique to humans. Many animals use tools. Crows fashion hooks from wire. Sea otters use rocks to crack shells. Chimpanzees use sticks to fish for termites. Given enough time and evolutionary pressure, tool use could advance further. 4. Some dinosaurs were surprisingly intelligent. Recent research suggests certain theropod dinosaurs, especially the troodontids, had brain-to-body ratios comparable to modern birds. They had grasping hands, binocular vision, and complex social behaviors. Could one of these lineages have evolved further intelligence if they'd had more time? 5. The Cretaceous lasted 80 million years. That's 267 times longer than humans have existed. If intelligence is even remotely probable, there was plenty of time for it to emerge. 6. We wouldn't necessarily find fossils. As discussed, fossilization is rare. A civilization lasting 100,000 years would leave very few fossils. These points don't prove a pre-human civilization existed, but they establish that it's not impossible. Now let's consider the arguments against. 1. We found no artifacts. Despite extensive geological surveys, mining, and fossil hunting, we've never found anything resembling manufactured objects older than a few thousand years. No tools, no structures, no remnants of technology. 2. No anomalous materials. We haven't found concentrations of rare elements, synthetic isotopes, or unusual chemical signatures that can't be explained by natural processes. The PETM and other climate events all have plausible natural explanations. 3. Evolutionary constraints. Intelligence is metabolically expensive. Brains consume enormous amounts of energy. A species would need a strong evolutionary pressure to develop advanced intelligence and the right anatomy to exploit it. Dinosaurs lack the fine motor control humans have. Marine animals face challenges building fires or metallurgy underwater. 4. The rarity of human-like intelligence. Despite billions of years of evolution, human-level intelligence has emerged exactly once on Earth. This suggests it's either very difficult to evolve or not particularly advantageous in most environments. 5. The specificity of human evolution. Humans arose through a very specific sequence of events: climate changes in Africa that fragmented forests, forcing our ancestors onto the savanna. Walking upright freed our hands for tool use. Social cooperation and language co-evolve with larger brains. Remove any of these factors, and we might not exist. 6. Industrial civilization requires specific resources: coal, oil, metal ores. These resources are available on Earth because of specific geological processes. A pre-human civilization would have needed access to similar resources. And if they'd consumed them, we'd find evidence of depleted deposits. These arguments don't definitively rule out a pre-human civilization, but they make it highly unlikely. So what do scientists actually think? The overwhelming consensus is that no pre-human industrial civilization existed on Earth. The evidence against it is too strong, and